So, we talked about 4 system of important in the blast furnace. Now, we will talk more about the reduction of iron ore, and as you can see, hematite and magnetite, these are the two most stable phases of iron oxide. Boostite dissociates, it is not stable below 570 degrees Celsius, and also you are aware that reduction goes in a sequence, hematite to magnetite to boostite and to iron, and reductant for this is mostly the CO gas. So, which is produced by burning carbon at the TUL level with oxygen, then you get the CO as a reductant gas and the heat. Now, the sequence of reduction which occurs with some calculation, we will show how much utilization of CO can happen. So, from hematite to magnetite at 900 degrees Celsius, your free energy is about 105,131 joule. So, you are already aware about this delta G, we can put it minus RT log K, and K is the equilibrium constant for this reaction, and this sort of calculation we have done before. So, we can calculate the equilibrium constant at 900 degrees Celsius giving this value. So, which comes equal to 48,000 PCO2 by PCO, partial pressure of CO2, partial pressure of CO, that is the equilibrium constant for this reaction, and in terms of reverse, CO over CO2 is 10 to the power minus 5. So, very low that ratio, which means really very small amount of CO would be able to reduce the hematite, and if you look at this is almost negligible amount, this one. So, only a little CO can reduce hematite into magnetite when it is in equilibrium. So, second, that once you reduce to magnetite, again it further react with the CO, carbon monoxide, and reduces magnetite to boostite, and this is the reaction where free energy is given here. Again one can calculate the equilibrium constant for this reaction, which comes to 4. So, CO2 comes to 0.25, and this 0.25. So, once this is getting reacted, then this 0.25 minimum which is required the equilibrium, this goes to the reduction of magnetite, hematite to magnetite, and this is sufficient enough. And so, what we are having in the 0.25, which is coming from this reduction in, and out is almost 0 nil. So, which is quite sufficient to reduce the hematite into magnetite, and with the we will see the next one in is coming from FeO to Fe 2.3, and it goes to 0.25. So, this is also quite enough to reduce magnetite into FeO, because the equilibrium constant dictates 0.25, the ratio of this. And when after boostite, again for it reacts with carbon monoxide and gives iron at 900 degrees Celsius, and this is your free energy. So, for this the equilibrium constant in terms of reverse ratio of CO2 comes to 2.3. So, here CO2 ratio, this is the one which is coming from the TUR, and as you know we have talked about this minimum you need it about 3.3 sort of ratio to reduce this. So, but after the reduction it comes 2.3. So, that is the minimum which you need it. So, this is the one which is going to the upper zone where magnetite get reduced to boostite, and then that is 0.25, and that one goes to the another one, another upper zone where hematite reduced to your magnetite. So, that is how these ratios are coming over here. Now, so CO utilization factor you can easily calculate. In the first case is almost negligible. So, CO utilization is almost 100%. Then so CO utilization factor is given by this formula, sort of as you say efficiency also, percentage CO2 divided by total percentage of CO plus CO2 at 900 degrees Celsius. So, for the first reaction it is almost negligible. So, CO utilization factor is almost 100% for that. For the second reaction the ratio is about 0.25, which means 20% that has CO, 80% it has CO2. So, utilization factor for CO is about 80% for this reaction magnetite to boostite. And similarly for from boostite to iron found this 2.3 the ratio, and if we put that one, so this gives actually a 30% CO2 and 70% CO is needed, and the utilization factor of CO is only 30%. So, really you need a very high this one and 30% utilization factor of the CO, which we discuss about these numbers we mentioned before when we were discussing about the reduction of those system, but we did not say how did we get these values, and this is the calculation by which you can show it how one can get these values 100%, 80% and 30% CO utilization in the reduction of iron oxide. Now, we talked about this system. Now, we will talk in terms of different way about the reduction. So, as you know, usually coke is used for heat reduction and mechanical support, and it wants at the tier level and give the heat. Nitrogen is mostly just getting heated up and take the as a sensible heat, and this CO gives heat to the descending burden, which reduces the oxides and CO2 is formed, and these are some of the reactions which you are already familiar now. And below 1000 degree Celsius CO is unstable, that we saw in carbon and oxygen diagram also system. So, overall reaction if we put it this also you are familiar. So, this is known as gaseous reaction, because from carbon monoxide gas it is getting reduced. So, gaseous reduction, and you also call it the indirect reduction. But above 1000 degree Celsius CO is stable, and this CO reduce FeO into iron, and it gasifies the carbon gasification of Woodward reaction, which we discussed before. This is so it again forms the CO. So, overall reaction is FeO plus C equal to Fe plus CO. So, this is actually called the direct reduction, but it is not the carbon which is reducing directly iron oxide or boostite, it is via gaseous phase it is getting reduced, and that is why we said direct reduction. Otherwise, it is not that through carbon we are or carbon solid carbon is reducing it directly, that is not the case, as we had discussed before also. This reaction may happen just near the boss where liquid ion and in which you have some FeO present travelling onto the Koch matrix with the direct contact with the solid carbon, then this may occur, but this is negligible. So, mostly it is in the form of via gaseous phase. And now we will talk quite a bit about direct and indirect reduction. So, as you know, direct reduction we need a less carbon consumption, it is a endothermic. So, it needs the heat. Indirect reduction more carbon consumption, exothermic. And as you know, in the blast furnace carbon is the main reductant, and the aim always is to reduce the consumption of carbon, that is coke, and that is a very important thing. So, from that viewpoint it seems maybe direct reduction would be useful. Now, we will see how the consumption of coke may occur in this reaction or the combination of these two. So, let us take an example for first the indirect reduction. So, usually CO2 ratio is about 1.5 in that blast furnace, which we can assume that is quite usual. So, that is a product gas ratio. So, indirect reduction. So, if we assume this, now hematite is getting converted into iron directly, the overall reaction as we said in this one. So, and the carbon what we CO what we get it is getting by burning of the carbon. So, suppose x mole of carbon is burned and complete oxygen is utilized. So, essentially x mole of carbon reacting with so many mole of oxygen giving you the x mole of CO, and this so this x mole of carbon and this reaction, if you combine, what you get it Fe2O3 Xe half O2 equal to 2 Fe plus 3 CO2 plus x minus 3 CO. That is the adding them up, this is the total reaction by which you will get the iron. So, now CO2 ratio can be calculated from this x minus 3 divided by 3 CO2 ratio, and that as we have said 1.5 the ratio go to 1.5. So, x comes to 7.5, which means 7. So, now we can substitute this into the overall equation here. So, Fe2O3 plus 7.5 carbon plus 3.75 oxygen gives to 2 mole of iron, 3 mole of CO2 and 4.5 mole of CO and 1000 degrees Celsius. The enthalpy is about minus 200 kilocalories. Now, if we take the direct reduction which we said in the previous one, or directly when it, or directly Fe2O3 is reducing, let us say with the carbon instead of wood type. We know that CO2 ratio is 1.5. So, maintaining that you can balance the reaction easily. So, here you will see the CO2 ratio is 1.5 and then remaining you can balance it. So, here your enthalpy is 75 kilocalories. Now, if we convert this one in terms of per kg, what we will find for indirect reduction you need about 0.81 kg of iron, and for direct reduction you will need about 0.23 kg. produce per mole of iron. So, which means that indirect reduction is giving quite high carbon coke consumption. Now, we will talk about another point here, and that is again we are taking an indirect reduction, but now what we would be considering, we would be considering different process. So, different process when we say one is, blast furnace is a counter current reactor. So, gas is coming from the bottom going up and the charge is coming from the top. So, it is a counter current reactor. Now, suppose both gas and the charge you are feeding from the top or from the bottom to then usually you call it co-current process. So, now we are considering that Fe2O3 and CO. So, before coming to this, now Fe2, you need a CO-CO2 ratio almost negligible to reduce hematite to magnetite. Then you need 0.25 from magnetite to boostite and boostite to iron, 2.3 at 900 degrees Celsius, assuming the ratio in the product gas is 1.5. So, in co-current process, when hematite and carbon monoxide, these are being fed together from the top. So, that is how the input is. Then it has to of course reduce hematite, magnetite, then boostite and then iron. And remember, when if you have to reduce the iron, your CO2 ratio has to be minimum here that 1. So, product can come to 1.5. So, you have to maintain this from here to here this much ratio, though your hematite magnetite reduction they do not need this high ratio, but because it is going in a co-current basis. So, here when it reaches it has to have a very high ratio. So, now if we do a sort of a mass balance on per mole basis. So, from let us say Fe2O3 to Fe3O4. So, 1 mole of hematite and x mole of CO is reacting with this, giving 2 mole of iron and bimole of this, of course, you can see from one of these reaction which we had before. So, giving y mole of CO and x minus y mole of CO2. So, that is a normal mass balance, you can do it. Now, based on this you can do the oxygen balance and CO2 balance. So, oxygen balance here 3 and 1 in the CO. So, 3 plus x equal to y output plus 2 x minus y. So, 2 terms, so that 2 x minus y. So, similarly you can do the CO2 ratio, and that is, as we have mentioned, is 2.3. So, and if you solve these two equations now, oxygen balance and CO2 from this, what we get x 9.9 and y 6.9. So, this is when hematite is getting reduced to iron, you need 9.9 mole of CO and 6.9 mole CO comes out and 3 moles of CO2. So, 9.9 moles of CO for 2 moles of iron, which means almost 118.8 gram of carbon for 112 gram of iron. So, which is about 1060 kg of carbon for 1000 kg of iron. So, you need this much, not actually this much coke. Coke would be higher because in the coke you have around 87-88% fixed carbon. So, if you are talking in terms of coke, that would be quite high, but as such in the carbon form you need more than 1000 kg, almost 1100 kg of carbon to reduce to get 1000 kg of iron for if you are going on a co-current basis in that. So, that is a very expensive and not a good process. Now, if on the other hand the way blast furnace works, it works more on a counter current basis. So, where the your output oxygen, as you can see, CO is feeding in from the iron side and hematite is feeding from the top and CO2 is coming out. And so, you have to maintain, and because the burning of coke is occurring here and which produces CO with a very high percentage. So, you already have that high CO2 ratio. So, which will reduce the FeO into iron. So, if we look at now in that way, so FeO to Fe 1 mole of iron. So, that is input and CO is your coming from the other direction. So, FeO is coming from the top and CO is coming from the bottom, and as you know, as I said before also, it needs 3.3 moles to reduce it in that one, and by the time it comes it can be 2.5. So, and because this CO is coming from the TUA levels, so you have a very high CO atmosphere which is coming. So, that easily satisfies this requirement. So, now we do the mass balance. So, 1 mole of x mole of CO is giving you 1 mole of iron and y mole of CO and x minus y mole of CO2. So, if we do again like oxygen balance, so 1 plus x equal to y plus 2 x minus y 2. So, and similarly CO2, it is from here it comes out 2.3 as we had mentioned before. So, this ratio is 2.3. So, it gives you x 3.3 and y 2.3. So, FeO to Fe you need 3.3 mole CO to react to give 1 mole of iron. And now we go from Fe3O4 to FeO. So, again now CO2 is or CO2 is coming in from this side and magnetite is coming from the top, and the output of this is FeO and output of this CO2 of that. So, now again we have to do the oxygen. So, this we know and now we have to calculate what we are going to get as the output of the gas. So, if you do again the oxygen valence for this in the same way, you will get 4y3, this is actually the table 4y3 and 2.3, this is because we are already previous calculation we know how much CO is coming in. So, that is 2.3 moles that we just calculated, 2.3 is coming in. So, and 1 mole of CO2 is coming, that is why we have put this. And so, we know input what is there and output we do not know how much CO is utilized, and so remaining would be the CO2. So, if we do the oxygen valence, so that 4y3 then 2.3 into 2.3 is oxygen plus 2 equal to 1 oxygen plus X plus 2 into 3.3 minus Y. So, if we do this valence, we can get the value of X. So, that is going to give us about this equation when we balance it, and CO2 ratio of this after the magnetite, when it comes out, it about 1.48, and when it comes out what it is required about 0.25. So, this is much greater than that. So, it satisfies even that condition of reducing Fe2O3 to Fe3O4, that one. So, Fe2O3 to now we got these moles from here. So, that is input Fe2O3 to Fe3O4, and we can, so our input is this is actually this is a oxygen 1 half one mole basis. So, because it is a 2 mole, so half, so would be that ion. Same thing about here, and these values are coming from our previous calculation, and same way we can do it our output one as we did before, and we do the oxygen valence, then X comes to 1.8 and Y then can be calculated. So, this gives you this equation where 1.97 moles of CO is being used to reduce hematite into magnetite. And if we do the, so this is overall mass balance of that one when we get it, if we put it all these values. So, this will be the overall mass balance of on mole basis, and so you can see 3.3 moles of CO for 1 mole of iron and 3.3 gram atoms in one way for 1 mole of iron, or so many gram of carbon for 56 gram of iron. So, for 1000 kg you need about 707 kg of carbon. So, what it is telling in the indirect reduction in a counter current condition, you need only 707 kg carbon to get 1 ton of iron. So, that is quite almost more than 30% reduction what we have for the indirect reduction for co-current condition. So, counter current, that is why we use the counter current reactor to produce carbon such as blast furnace. Now, if we go to the direct reduction, so direct reduction, as we talked about this equation, you can directly calculate how much is the coke requirement for 1 ton of iron. So, you get about 322 kg of carbon for 1 ton of iron. So, that is looking at it for counter current indirect reduction, and direct reduction, there is a big difference again in the coke consumption. So, this coke you can save it. So, in one way direct reduction is quite beneficial in terms of saving the coke or carbon than indirect reduction. So, here we assume 100% indirect reduction, here we are assuming 100% direct reduction, but you need heat supply for this. So, if we put a summary all together, so for co-current we need 1060 kg per ton of iron, for counter current we need about 707, for direct reduction we need about 322, and if we put a combination of these direct and indirect, you may see probably we can substantially reduce the carbon consumption. We will now see this calculation, how do we arrive on this 165 kilo kg of carbon for per ton of iron. So, this is now for the direct plus indirect reduction, combination of both. So, if we say x mole of carbon is directly reducing iron oxide to iron, and remaining of course would be your indirect reduction, that the CO would be reducing bauxite to iron. So, now if we do the balance again, we can make the mass balance table. So, 1 mole like your input, if we do for this x mole of carbon, you get the output 1 mole of iron. Actually finally when it reduces, you combine it and you will get the COX. If you combine these two, then you can do the mass balance, then you get x minus 1 minus x equal to 2x minus 1, CO2 is 1 minus x and 0 carbon as an output. So, now if we look at CO2 ratio, for this you know you have to maintain about 2.3 as we did before, we had mentioned about it. So, that gives you x equal to 0.77, which means about 77% FeO will get reduced directly with carbon, and will give you that, and remaining 23% FeO will be reduced by carbon monoxide, that is indirect reduction. So, and when you put this value, then you will get 165 kg of iron is needed per ton of kg of carbon is needed for per ton of iron, and that is the most beneficial economical reaction. But how to achieve this? This is a challenge in the blast furnace. How can you control that 77% should be FeO and 30 by direct reduction, and 23% should be by indirect reduction. But one can play around with this figure and can certainly achieve a good saving in the coke consumption. If you look at now the modern blast furnace becoming large and large, and they are trying to reduce the coke consumption, playing with these sort of figure. So, as you can see now the coke consumption is about 300 kg or so in the modern blast furnaces, and then of course, you have a PCI injection. So, which is if you look at it lower than probably some time of this your direct reduction. So, in that way probably you are playing between these two direct and indirect reduction and trying to optimize, but certainly there is always a room where this can be optimized and carbon consumption can brought it down further to save the coke consumption in the blast furnace. So now, so again checking whether this whatever we have discussed, this COCO2 is sufficient to reduce magnetite to FeO. We can do the balance based on what we quoted here 0.77 and 0.23, then it should be the CO2. So this balance can be easily done as we have done before. So I will not go much into the detail. Oxygen balance and would be this. Okay, I think one should be here, which is missing. So that will gives you 0.207. And when we look at the CO2 ratio, it's about 0.367, which is greater than what is required. So that even CO2 ratio is sufficient to reduce the magnetite into bushite, and certainly then it would be possible even to reduce the hematite into magnetite. So this is again checking after this, is it sufficient to reduce the hematite into magnetite? Again, if we do the balancing act, we will come to the same thing. So here 3 to the oxygen, which we are getting output before Y3, and this should be the so X comes 0.04. If you do CO2 ratio, then 0.04, 0.73, it comes to 0.055, and really it's a more than negligible what we needed from hematite to magnetite. So it's quite enough that ratio to reduce the hematite into magnetite. So with this sort of 77% and 23% ratio from hematite to iron, you have sufficient CO utilization factor or sufficient CO to reduce it from top to bottom and get the iron by consuming only 165 kg carbon to get per ton of iron.